a practice session.
Oh, yeah, good point. I have to do that too. There's like 15 things I need to click on, which I just did. And we are live, Jeff.
Great. Thanks, Chris. Welcome, everyone, to Your Rights, Your Bites, a weekly live discussion and podcast about ownership, digital rights, and privacy. Today, I'm here with my co-host and partner in crime, Christian Kamir, a managing partner at Sustaining Capital, a VC investment fund that focuses on blockchain. Christian has been doing phenomenal work on the future of money and understanding the problems of central bank digital currencies. Say hello, Chris.
Hey, I'm still managing my video and audio engineering skills. Hence, if you're seeing this on YouTube right now, you see that I'm messing up.
I do see that you're playing with that. Let me go ahead and I'll continue on. So I'm Jeff Jokish, the founder of Privacy Plan, and a vocal privacy data researcher, a data privacy researcher. And today we're talking about biased machines and prejudiced programming. That's quite a topic, a wide topic, a deep topic, and one everyone's who's concerned with privacy should really be thinking about. The connection between privacy and AI might be unclear to some people, but all of that personal data that organizations collect about us has to be processed in some way, really, to have value. And we often think about that processing as maybe targeted advertising, because that connection is really right there in front of us. But our data gets processed in more complex ways as well, in social media algorithms, by government agencies for services, insurance companies determine coverage and rates, sometimes courts to determine sentences, doctors to determine treatments, and much, much more. What's even scarier is that these processes using our personal data are often black boxes. And what's even black boxes predicting things about us. Possibly, these are very accurate predictions, but exactly what data are they using? Are these decisions fair? How would we even know if they were biased? Today, we've got two guests with us. Ryan Carrier, who's the Executive Director of For Humanity, which you can find at forhumanity.center. And their sort of focus is to examine and analyze the downside risks associated with ubiquitous advances of AI and automation, to engage in risk mitigation and ensure the optimal outcomes for humanity. Right? And then we've also got Krishnaram Kenthapati, the chief scientist at Fiddler AI, who we are trying to bring up to the stage, I think, when Chris gets the video set up here. Okay, are you on stage there with us?
Yeah, he is.
Awesome.
Yes. Hi, Jeff. Thanks for inviting, and very nice to meet you all and be part of today's discussion.
Awesome. And Fiddler AI really does sort of model performance management, helping orgs monitor, explain, analyze, and improve their solutions to build trust into AI systems. And we'll let each of these gentlemen sort of do a little bit more talking shortly. But let's open up with a quick presentation by Ryan Carrier. Ryan, tell us a little bit more about yourself and help us answer this question. How do we know when an algorithm is fair?
Thank you, Jeff. Thank you, Chris, for having me on. As you mentioned, I'm the Executive Director of For Humanity. We are a nonprofit public charity, 501c3, mission-driven, We are an organization that up until about 2 years ago was pretty much just me trying to figure out how to help or how to mitigate these risks. And over the last 2 years, we've grown incredibly. We are now nearly 1,000 people from 70 countries. We've built and crafted over 6,000 lines of audit centered around this concept of independent audit of AI systems, designed to mitigate risks, as you mentioned, from AI, algorithmic, and autonomous systems by creating a system of governance, oversight, and accountability around AI and algorithmic systems. And so our primary mission is to craft these audit criteria, submit them to governments and regulators around the world that are jurisdictionally sensitive, fits into the laws of their lands, but also identifies best practices, standards, guidelines, regulations, turns them into auditable rules so that we find ways to be able to externally verify them with independent auditors, and thus creating an accountability and governance structure that is far more robust than what exists today. And so to tackle your question, Jeff, we identify 5 pillars: ethics, bias, privacy, trust, and cybersecurity, trying to capture all of the negative impacts and outcomes that impact humans into these 5 pillars. And obviously bias, which could be translated into discriminatory practices or fairness, to answer your question, is one of those key pillars. And here's the answer: you'll never know that an algorithm is completely fair, and complete fairness is probably an impossibility. So we want to be careful about how we answer this question and try to maximize a couple of things. Number one, we want to maximize fairness, broadly speaking, and we'll talk about some measures for that. We want to mitigate as much bias as possible, and we do this in 3 different ways. We mitigate bias in data sets, we mitigate bias in architectural inputs to models, and we mitigate bias in outputs and outcomes to humans. And this is done on an iterative process. It includes both statistical requirements. It involves decision-making and structural inputs to the system, but it also involves instances of ethical choice, where it's not a right or a wrong answer. It's here's the decision or the conclusion we made that we have satisfactory representativeness, let's say, in an algorithm. And so all of this is combined to mitigate risk to the best we can. And then on top of that, we require a whole mess of disclosures and transparency and explainability and explainability plus. We require all of this to help facilitate increased fairness of all of these models, where we celebrate the human dignity. You used a term at the beginning talking about how these systems interact. We use the term socio-technical. And the reason we call these systems socio-technical is the human is part of the equation. Not like a calculator, you punch the numbers in, the calculator does its thing, and it comes back to you, right? The human is in this equation almost every time. And those are the systems that For Humanity cares about. And because they are socio-technical, we do have to include ethics. We have to include fairness. And the last thing I'll say, and then hand it over to the rest of the panel to chit-chat about, is we do have a few metrics of fairness that continue to arise. The one that is most tested, and in fact has gone to the Supreme Court twice, is the 4/5 rule that's used in hiring in hiring in general, to basically say that as long as 4/5 your selection rate you start with your highest selection rate, and then as long as all protected categories are within 4/5 of that selection rate, then you can argue that you do not have disparate impact to any of those protected categories. Now, there's nothing magical about 4/5. That's 80%. There's no magic in 80%, right? 81%, 90%, 75%. I don't care. Don't care, really don't care. The point is have some thresholds, introduce some metrics that basically say, look, you might have the risk of bias. You might have the risk of unfairness. And in those cases, let's talk about, explain, disclose, and demonstrate the actions that have been taken to mitigate bias and to enhance fairness in those systems. Hope that answers your question, Jeff.
Yeah, that was actually a really pretty great answer. Can you explain a little bit further, Ryan? Because I don't think a lot of our audience knows, and I guess a little bit privy because I've been on the inside of For Humanity. How is it that For Humanity sort of helps the world, helps humanity with this audit process? Because I don't think very many humans understand that yet.
Well, let's take an extremely simple example first. You, Krishna, Tim, Chris, everybody on here might try to build or do things in an ethical fashion. Most people want to operate ethically. And we do that as best we can. And then we get distracted and we get busy, or other things get prioritized, and we don't necessarily finish our work. And we don't always maintain, let's say, documentation and so on like we should. This is the problem and weakness of self-assessment. So the first and most important principle of independent audit of AI systems is that we as humans behave differently when we know someone is watching. Jeff, I know that if you're going to come in and check my work, I will do it and have it done to the level that it needs to be. This is simply human nature. And so what we end up doing and constructing is really 4 lines of defense. When you create a set of rules that replicate and demonstrate compliance with laws, now you can teach and show even designers and developers how to achieve compliance. And then we have a management layer that checks on compliance and affirms compliance and handles management style decisions. And now we have a second line of defense. A third line of defense is internal risk and controls, where they're basically outside of these working groups, these product development teams. And they say, look, we want to abide by these rules. Here's our list of controls. Here's the list of checks and balances. Here's the documentation and transparency that's required. Are you achieving that? So these are 3 lines of defense. They are all internal to the company. Now, what's unfortunate is that we are still internal to the company. So we could be swayed by costs, benefits, profitability, and so on. And that's why we have to have this 4th line of defense, external verification. And it's very simple. When we set up independent audit of AI systems in the right way, where auditors are conducting audits not with a client. Audits aren't done with clients, auditees. They're done over clients. And they're done actually not on behalf of the client. They're done on behalf of a third party. Do you know who that third party is? The public. It's where the public says, these are the rules of compliance we want to see. And the auditor says, well, the public can't do this. I'll act as a proxy on behalf of the public. And I'll do this in an independent way. Independence means they have no remunerations other than their audit fees from this entity to maintain objectivity. And they have the risk of false assurance of compliance, meaning if they tell people that there's compliance and there is not compliance, they're on the hook as the auditor. And when you set up this tension between the auditor and the auditee that is independent and objective, now when that auditor says, you know what, Jeff's company has complied with all of these rules, you know what the world believes? It must be true. Yeah. And this is how we create an infrastructure of trust. And we're replicating a system that's been around for 50 years in independent audit of financial accounts and reporting. And people will say, well, is that a trustworthy system? 99.9999% of the time, things go great in independent audit of financial accounts and reporting. Entire businesses, entire industries, entire investment strategies rely on these numbers, often without even checking them. And that shows you that there's an enormous amount of trust. But I also want to caution, there's no perfect system. Anytime you come out with a transparent rules-based system, you are teaching people who want to commit fraud and malfeasance how to defeat that system. So let's go into this with eyes wide open. This is a great system built with independence and checks and balances, removals of conflict of interest. But there are no perfect systems, and we don't anticipate that this will be. But let's be clear, in the most famous accounting disasters ever, Enron and WorldCom, it was actually still the system that caught them out through transparency and disclosure over time. And so those are the kinds of checks, balances, procedures, controls we want to build into this whole ecosystem to better ensure that we mitigate risks to humans. Long answer, Jeff, I apologize, but hopefully hopefully it's a good, a bit of an explanation.
No, I think that was a great answer. And frankly, I really love the system. You know, I've already taken one of the classes. I didn't take the test yet. So I love I love what you're doing.
Let me offer one disambiguation here at this point in time, maybe. So because I see this a lot. So I was an engineer before I became a lawyer, and now I'm neither. But the point here being is what I see on a daily basis is a conflation about the concepts of rules and laws. So what I mean by that, we call certain things laws that are really just rules. And so the difference here is, so there's rules address human behavior by and large, right? So and laws are things, at least in my definition, that are true regardless if you follow it or not. Like things like gravity. You can ignore gravity, but it's a good rule to follow it because it's an actual underlying law. When you ignore that law, you always fall flat on your face, right? So it's kind of a fact-based thing. And so that's how I think about technologies. Technologies establish laws. They function in a certain way. You put an input in and an output comes out, and then you can either, as a human being, follow that particular output or ignore it, whatever the case might be. And so that's where I think we have a lot of kind of vacuous discussions about regulators that say nonsense, like I want to regulate cryptocurrencies, I want to regulate privacy. What they're really saying is I want to regulate the behavior of people within my jurisdiction. That's all you can do at the end of the day. And then ultimately what we need to do as people who kind of translate this to engineers is like what you want to develop is systems that actually create laws that are human, as in they obey the objectives of the human, rather than you needing to fall back on something that then requires the nation state to enforce its rules rather than its laws, what they call laws. Anyway, I just wanted to offer that because I see a lot of vacuous conversation happening in this realm all day long where lawmakers think that they can change gravity or cryptocurrencies or something else by making new rules. But I think we should invite Krish to... Can I call you Krishna Ram? And you need to unmute.
Yeah, Krishna Ram or Krishna would be
Krishna? Okay, I like that.
Yeah.
All right, because I don't want to butcher it. So do you want to tell our viewers and listeners what you're all about?
Yeah, sure. My name is Krishna Ram, or Krishna for short. So I'm the chief scientist at Fiddler AI. We are an enterprise startup building tools for explaining machine learning models, identifying any biases in the models, and monitoring the models once they're deployed in production. So maybe I'll kind of take a step back and kind of start with why we are doing all this. I think Ryan provided a great introduction into some of the challenges that we are facing today with machine learning models, primarily from an angle of auditing, compliance, meeting regulatory requirements, and so forth. In addition to all of this, there are also aspects which come from the angle of even say data scientists or product managers or business decision makers, even within an organization. Today we have a situation where there is a lack of enough transparency of the models. So by transparency, what I mean is even the developers or the data scientists who come up with a model themselves may not be in a position to understand how the model functions. The analogy I would like to draw is if you take, say, techniques for training machine learning models, there are techniques such as stochastic gradient descent. There are techniques to train different types of models, maybe deep learning models and traditional models. If you look at these techniques are relatively simple to describe, and for somebody who is proficient in the machine learning field, they would not have difficulty understanding these techniques. But the challenge is when these techniques are applied on large amounts of data, the resulting artifact is the machine learning model. Often these models may have, say, thousands or millions of, or sometimes even billions of parameters. And in the case of what are called deep neural networks, then they may be several layers deep, to such an extent that even the model developer would not be able to comprehend how the model behaves. That is one challenge the various stakeholders are facing. So how to understand the behavior of the model, both as a whole and also when it makes predictions for specific inputs. The second aspect is more from an operational angle. Often there is a lot of emphasis on validating the model and vetting the model before it gets deployed. So when, say, let's say a data scientist trains the model, either the data scientist or with the help of, say, compliance or legal teams, there may be a lot of effort that goes into vetting these models, maybe testing these models for performance for different groups, for bias, and so forth. But once the models are deployed, there is an assumption and hope that the model will continue to perform as well over time, but often that's not the case due to various real world conditions and changes. For example, COVID pandemic or any other changes over time, the behavior of the models may not be the same in production as it was during training. This is important even before any auditing or regulatory angle comes in. Like even from a purely business or profitability or revenue perspective, often companies are interested in this. How to make sure that the model remains of high quality and performance over time, not just while it was trained or before it was deployed. This is one of the aspects where we provide functionality to monitor the models once they're deployed. And of course, we not only want to monitor these models for performance as a whole, but also whether they perform well for all different groups of interest. In the cases of models that have an impact on humans, we would like to understand whether the model is performing well for different demographic groups or people with different interactions or experiences with the machine learning system and so forth. The final element is around, say, bias and compliance. We want to understand whether the model works well for different groups, both at the time of model training and even after it's deployed in production. So we also offer tools related to monitoring of bias and also measuring of bias. So in this regard, maybe one of the challenges that Ryan also alluded to, and is something that we encounter is dimensions like fairness, privacy, or explainability, transparency, or intrinsically socio-technical. They're not just purely technical concepts. In fact, if at all, there are more of the social aspects. So that means that we have to take inputs from all relevant stakeholders, including those who are impacted by the decisions of the model, to decide what is considered fair, what is considered acceptable in terms of the level of privacy or the level of transparency, and so forth. And here again, one of the challenges is that if you take a domain like privacy, even the attendees of this session would collectively agree that protecting privacy of users is important, but we might possibly disagree on the trade-offs between, say, the accuracy of the model and the level of privacy protection it offers. But when it comes to a domain like bias or fairness, things get harder even at this stage. Even as a group, we may not agree on what is the desired notion of fairness. As we discussed earlier, there are often tensions between different notions of fairness, tensions between being fair at an individual level and being fair at a group level. And even at a group level, there are results, theoretical results showing that it is often impossible to achieve fairness along multiple dimensions. We cannot achieve fairness on, say, accuracy, fairness on false positives, fairness on false negatives, and maybe a few other metrics together. So that makes the problem even harder and more challenging, both from social and technical angles.
Yeah, that's really, really interesting. I think, Krishna, that you sort of answered the question that I was going to sort of pose to you, which is it possible to create algorithms that optimize for both accuracy and explainability? And I think what you're sort of saying is that the answer is sort of yes, sort of with your help and maybe with Ryan's help, because you guys sort of both come at this question from two different angles, right? You're sort of helping them with the model, and Ryan's sort of helping them audit the model, right? Let me give you a little bit more context to the audience. Last year when I was researching AI regulation, I boned up a little bit on explainability, because a lot of the regulations start talking about explainability. Some are even trying to mandate explainability in the AI models and algorithms, right? And frankly, explainability was a little bit new to me, even though machine learning is not. I've managed data science projects and helped build some pretty large Bayesian classifiers that use supervised learning to assign topics to text messages. One thing that I found that was interesting, and maybe even a little bit bleak, is that there's some DARPA research that shows that in general, machine learning models that are more advanced, more complex, more accurate, are also more black boxy. They're less explainable, less transparent, right? So in layman's terms, if companies use the most accurate predictions, they're probably sacrificing explainability and the ability to tell people what the hell's going on in there, right? They understand the models less well, and they don't really understand why the models predict what they do. So I imagine some of you guys have seen the HBO series Silicon Valley, right? In the show, someone developed an algorithm that can tell if an image is a hot dog or not a hot dog, right? And this seems pretty useless, at least in the show, right? Until they decide to repurpose it to be a porn filter, which was pretty valuable, that it turned out, right? But here's the thing, right? How does the algorithm actually know whether something's a hot dog or not? I mean, you guys know, if you understand machine learning, right? You test it with a lot of images and it eventually learns, right? But how does it learn, right? Is it the reflectivity? Is it the shape? Is it this or that? I mean, it's probably thousands of little things, right? How do you actually explain that to someone? Right? It's pretty hard, right?
Yes, I think that's a great segue. I think there is, as you kind of alluded to, there is often this tension between interpretability, or how easy it is for humans to inspect the model, versus how performant the model is. This tension arises especially in the domains related to human cognition, domains like maybe vision, say object detection, or classifying some visual, or say images or videos, or say domains like speech to text or text to speech, language translation, and so forth. So the challenge is that simple models, say, let's say rule-based models, or models that are called decision trees or linear models with a small number of parameters, are easy for humans to understand. But what has been noticed in the last decade or perhaps more is that such models are not as good when it comes to tasks where humans are really good, tasks like human cognition related tasks. And for such tasks, what has been noticed is that models which involve several layers of neural networks, what are called the deep learning models or deep neural networks, tend to perform well. But the challenge is these networks may behave in a way which may not be intuitive to any of us as humans. So there is a lot of recent work, academic work, that has gone into understanding how these networks themselves are functioning. Can we even take such neural networks and provide semantic meaning to how, say, different layers are behaving? There is some work in that respect. For example, alluding to the image detection tasks, there are papers which describe that different layers of a neural network capture maybe different aspects. Let's say at the initial layers, there may be capturing of perhaps the boundaries between objects, like say curves and lines, and later layers may be more complex patterns or concepts, like say the patterns of a zebra, or the how, let's say, different objects typically are structured and so forth. And at the final layer, perhaps it corresponds more to each object in terms of how these patterns come together to represent a particular object. At the same time, there is also literature, there's also a lot of work on taking such accurate but opaque models and providing explanations post hoc. By post hoc, this means more as a layer on top of the output of the models. The idea is that these models may be hard or complex to understand as a whole, but at a specific point of interest, let's say at a point of interest such as whether we are trying to detect why, say, some object was detected in the image. Let's say if you think of an autonomous vehicle setting, why a pedestrian is detected or a stop sign is detected, and providing an explanation of that just for that specific image or around that image. There is a lot of work in that respect which is getting traction. This whole line of post hoc explanations is getting more and more traction, partly because it helps balance both ensuring accuracy using these opaque complex models, and also providing some level of human understandable explanations on how the model is behaving.
Could you apply that post hoc analysis to something like, whether a job applicant was accepted or not accepted?
Yes. So in a setting like, say, a job applicant, often the approach followed is what's called counterfactual explanations. This means that let's consider the case of a job applicant who was denied a job. What attributes would have needed to be different for the model to change its prediction? So to kind of arrive at the counterfactual. Or in the case of, let's say, somebody applying to a loan and the loan application being denied, what would they need to do to qualify for the loan in the future? So this is kind of similar to how today we get adverse action notices. If say in the US, if you apply for a loan and there is an adverse action, then legally you have to be provided with a reasoning as to why that has happened. So even with the case of machine learning models, whether they're used in hiring, lending, or other settings, there is a possibility of providing such explanations. But I don't think we are at a stage where it's perfect and maybe completely auditable. There is work showing that if the organizations who are owning the machine learning models or coming up with such counterfactual explanations, they may be able to come up with explanations which look great on the surface, but might hide some of the biases and issues that the model still might have.
That's interesting. Yeah, I was just going to say, Ryan, what do you think about this, the counterfactual concept?
Two elements of that. So counterfactual, the exact example that Krishna gave us of counterfactuals, we call explainability plus. So it's probably worthy to define the spectrum. We view it as a 4-tier spectrum. It's built in compliance with GDPR and the EU Artificial Intelligence Act as it's currently drafted. Interpretability is a technical term reserved only for the entity, and it's understanding the hyperparameters, inputs, outputs, et cetera, so that those technicians can feed back in and tune the model. So for us, that's interpretability. The EU Artificial Intelligence Act calls for something else that's still at what we would call an institutional level, and that's where you have to have sufficient interpretability on dysfunctions, anomalies, outcomes of the system to give to users of the system. And when I say users, we mean the technical users. Azure produces an AI, and HSBC is going to embed it into a customer service model. Okay, so HSBC has to have this technical interpretability. We call it exceptions interpretability because it's demanded to understand the exceptions that come out of the existing model. Those are technical, those are institutional level. Then we cross the barrier to explainability. Explainability is the law under GDPR. It is also the law under the EU Artificial Intelligence Act. It's also the law on fair credit and lending, for example, as Krishna mentioned in finance. And so explainability is now the clear and plain language explanation of why an outcome occurred. Now, people who get acceptance or get positive results, they never care, right? You don't have to tell me why I got it. That's what matters, right? So really, we're only focused on those negative outcomes to humans. And thus, it's also, I mentioned kind of tensions before, early on, right? This is a tension. The human has now gotten something that they were hoping to get a good result and they did not. And this is where we think explainability falls short. Because telling somebody why they didn't get something doesn't help them. It really doesn't. It might make them feel a little bit better. They might be able to look at their checklist of things and be like, yeah, I guess I didn't qualify. But you know, it doesn't really help them. And that's where we move to explainability plus. And we want to celebrate the human dignity. And we want to do exactly what Krishna said, is we want to actually explain and educate how, if you want to have another interaction with this model, how can you improve? How can you make your situation better so that you might have a better interaction? Now, under Explainability Plus, what have we done? We've created companies and people working together. That builds trust. That builds a relationship. That helps position someone into a better place where they might get a better result the next time around. Or part of Explainability Plus might be, look, you're never going to qualify for what, for what we require, but here's some other outside external services that you might be able to avail yourself of that might help you solve your problem. This is a human-centric approach. The law doesn't go quite this far. We advocate that it should. Obviously, we're for humanity. That's what we do. But we also think that this is smart business. This is sustainable profitability when you begin to engage with clients in a way that will result in a better, more trustworthy interaction. And that's why we advocate for Explainability Plus. However, the other piece of this that I want to identify is that no model is perfect. And therefore, false negatives are a legitimate issue with all model development. And so we are, in our audit criteria, requiring a level of false negative acceptance in model development. So that basically what this is you would have denied someone a loan. But because of your requirements to actually have some false negatives in your outcome set for proper evaluation, you should consider actually granting those loans, so that you can learn in your model feedback and your pipeline quality if your false negatives are actually just negatives, right? And not false negatives. And so what it allows for you to do is actually get better feedback and better information into your learning models and improving the models in general through greater validation. And the last thing that I would say is we require, when it comes to testing and evaluation, we require the analysis, as Krishna mentioned, at protected category levels, including intersections thereof, for industry standard acceptance of accuracy, but also where there's sufficient construct validity, causality, and ground truth validation. And these are really more as we talk about socio-technical systems, these are more socio-technical ethical kinds of considerations built into these models, because there are models out there that just take a whole bunch of stuff and reach conclusions without that interpretability, without that explainability, but because they have, by their own measurements, high accuracy, high validity maybe, they're actually putting these models into place. But it might be something like, you, sir, have glasses, you're wearing a coat, and you live in Florida, therefore you must be a New York Yankees fan. And you're like, what? How did we reach that conclusion? But the model, is able to reach this conclusion, but without that causality, without that ground truth validity and validation. And so these are steps that we have to do to improve our model production. NASA recently came out with a whole list of AI ethics guidelines that they're going to grow into, and they're going into an NTSB kind of model. They're basically saying, look, everything we do is high stakes, everything we do is at risk, and therefore we can't have accuracies of 60, 70, 80%. 90% is too risky for us, right? And so what that means is they have to get to a place of testing, the same place that airlines have gotten to. Test and test and test and test and test and test and test again under all sorts of adverse conditions, under each kind of variable, under every kind of edge case examination before they can put these models into place. And embedded in that is this construct validity, is this ground truth validation. And so I actually reckon that we will get closer and closer to those kind of models when we're talking about high risk applications, not meme generators, not funny little AIs, not cute little recommendation engines, but for things that really impact humans and have legal impact, have life and death kind of considerations. All our models are eventually going to get there, but we've got a process to go through and a long way to go to get there.
Yeah, and ultimately,
it seems to me, Ryan,
on
I love your explanation there, but it seems to me that if we talk about this counterfactual generation that Krishna talks about, and we sort of mix that with the explainability plus that you're suggesting, that the combination of those two ideas, which maybe are really the same idea, that if companies are actually implementing that it's actually going to point us to all the bias that would be in a model, right? And have us be able to figure that out and fix it.
Absolutely. It's one of those three elements that I talked about. We're going to analyze data, and we have a whole series of steps to improve and mitigate bias, right? We have the architectural inputs, overweights, underweights, protected category variables in the construction of these. We can examine inputs. One of the reasons that we take this approach is that if we examine architectural inputs and we examine outcomes, we can let the black box exist in the middle. And I think there's a robustness to that because there are a number of models. I mean, take some of these large language models where there's so many billions of calculations and nodes that tracking that process may become burdensome, cumbersome, or impossible. But if we look at the architectural inputs and those outcomes, then we have this ability to sort of say, well, I kind of don't care what you did in the middle because we're going to catch it in the outcomes, or we'll catch it on the way in, right? And so in examination of those outcomes, and by the way, bias is the least mature of those 5 pillars that I mentioned, right? We have a long way to go to figure out different ways to support fairness and to mitigate more bias. But we can take steps like explainability plus, like 4/5 rules, like looking at the impact on protected categories and intersections thereof, to help us identify and thus mitigate bias by iterating the system. One other key thing, and Krishna Ram kind of touched on this as well, I want us to make sure that we understand the very nature of most of these models is to find normal, right? It's to find a fitness of the model to a data set. You know what people aren't? Normal. There are a lot of people who exist on the edge cases. And by the way, a lot of those are people who are in vulnerable situations. And so inclusion is a natural, I'm going to use the word counterbalance for a second here. You can go for a highly accurate model, but you have to eliminate some of those outliers and some of those anomalies. And you know who an outlier is or an anomaly is? Well, it's that disabled person, or it's that neurodivergent person, okay? And as a society, we've said, by the way, that's not okay, right? We have laws, we have the Americans with Disabilities Act and many others that increase accessibility and inclusion. And so what we have to do is we have to find out a way to have edge in thinking about these anomalies and about these outliers and help fit them into the model and then figure out what kind of accuracy we can achieve. And it's a give and take. I don't think you can achieve both. I would love to be proven wrong on that, but I think there's a difficulty in the way these models calculate and conduct themselves vis-a-vis anomalies and outliers. And in the end, if we have to go to accommodations, if we have to go to transparency and disclosure, this model does not work for you, okay? Then we have to make sure that those accommodations and that inclusivity is robust and fair. Does that make sense?
It does. I think that's a really important point you bring up on inclusion. Any thoughts on that, Krishna? Do you work with inclusion with any of your clients?
Yes, I think that's it's a great dimension that Ryan touched upon. So one of the things I often emphasize is that when it comes to, say, even domains like fairness or bias and fairness, there is both a technology element and a policy or a social element. Regarding the policy element, it starts with even identifying what are the relevant goals of this product. Do we have all the right people in the room? So by right people, I mean all potential stakeholders, especially the people who may be negatively impacted by this product or service. I think it's very important to have them in the room, and ideally have them have such representation in the team as well, so that you do not have blind spots. You have proactive testing and identification of cases where things might go wrong. Then the next step I would think of is, even when we start working on, say, let's say a problem, it's important to understand whether even is this problem an ethical problem to be approaching in the first place? Is this a problem for which applying machine learning techniques would be an ethical solution, or do we want to even take a step back and see whether this problem is something that we want to even provide technical solutions for? Then once we have decided that it is an ethical problem to be looking at, then the next step is, when we collect, say, training data for the machine learning model, do we have a representation of all relevant subgroups of interest, especially the corner cases, edge cases, as Ryan alluded to? In case we do not have enough representation, are there methods we can do to eliminate biases? Can we do methods to reduce biases in the data set? Maybe can we do perhaps oversampling or undersampling of people in the data set, so that there is enough representation of all relevant groups?
I wanted to ask about that. But somebody like you probably knows the answer to this. Maybe Ryan does as well. But so say you've got a facial recognition problem with your model not representing or recognizing Black females particularly well, right? We know that's an issue. So what if you add a whole bunch of Black females to your model, so that you're oversampling, I guess, for that, right? How does that affect the rest of your model? Does that make white males less understandable to the model?
This is a great question. In fact, one of the examples I was thinking of is, precisely about this. Like this problem was brought to light by the work of Joy Bolambini, who noticed that the off-the-shelf machine learning techniques were not working well for her own identification. Joy Bolambini is an African-American woman, and she noticed that when she wears a white mask, the model was recognizing her face, but otherwise it was not recognizing. Then together with Timnit Gebru, Joy Bolambini and Timnit Gebru came up with gender shades work, which kind of highlighted these issues and also provided benchmark data sets. There is, I think the short answer to what you asked is, I would say it depends. In some settings, there may be a tension between, say, ensuring performance or accuracy of the model as a whole and ensuring that the model works well for all different subgroups. But that's not necessarily the case. If we take even facial recognition or facial analysis as an example, what happened after gender shades? What was various companies woke up to this reality. They had not, my sense is that they had not taken the effort to do such thorough testing before these issues are discovered. Once they woke up to the fact, they were trying to figure out how to address these issues. One of the approaches was to collect enough data points from the underrepresented groups. In the process of collecting such data points, it's not as though it might necessarily affect the performance of the group, the model as a whole. It's possible that by improving performance for some subgroup, we might even improve the performance of the model as a whole. So say, think of a setting where, say, there is data from several different hospitals, and it so happens that the data from one hospital is corrupted due to some reason. If you just apply a machine learning model on this combined data, even though the model might seem to work well across the board, we might notice that it doesn't work well for certain demographics or certain types of people. But once we go and identify the root cause and then we fix those issues, the chances are that the model might work better on the whole, not just for that group. So I would say it very much depends on an application to application, and especially related to that, there is a recent line of thought called minimax fairness. So what this intuitively means is that we want to make sure that the worst of group is as well off as possible. Instead of forcing, let's say, a metric like accuracy to be the same for all different subgroups, the goal here is to minimize the worst case error for any group. So in the process of doing that, in the process of minimizing the error for in the worst case for across all groups, we not only ensure that we capture those corner cases, but we also ensure that we do not artificially try to equalize the error by reducing perhaps the performance for a group for which the model was working really well. In fact, there is theoretical work showing that this approach of minimax fairness would achieve models which are strictly better than the models which force parity of errors. But of course, it's a social question as to whether we are willing to accept significant difference in error rates across different groups. That's less of a technical question, but from a technical angle, there are methods which ensure that in the process of improving performance for one subgroup, we don't necessarily affect or reduce the performance for other, especially the dominant groups.
And Jeff, let me jump on top of that as well.
Sure.
We can create a market-based mechanism that's going to sort that out for entities producing these solutions. If we introduce a residual risk model similar to the way the FDA releases drugs. So we've all seen in this country, you see that the commercial, there's the family and they're running through the woods and they're swimming in the lake and the sky is blue. And for the first 30 seconds of the ad, they describe what this drug will do for you. And then you get that second 30 seconds of the ad, and it's pretty equally split, and that's on purpose, and that's by design. The final 30 seconds are, and by the way, if you take this drug, you're going to have headaches, and you're going to have dry mouth, and you're going to have irritation at the spot, and you're going to get, sorry to be graphic, diarrhea, and you might die, right? They're disclosing all of those residual risks so that you, as an informed consumer of this drug, can recognize what the risks might be taken. And now you're informed, or at least reasonably informed, about whether I should take this drug or not. We don't have anything like that with AI, algorithmic, and autonomous systems, but we have to get there. Why? Because with this transparency and disclosure, what we're going to do is we're going to ask entities to accept a risk-based approach to what is sufficient accuracy at protected categories, at intersections thereof. And we're going to ask them to use and publish these models and disclose a residual risk. And by the way, if you put something out with too much residual risk, the market isn't gonna use it. And so now you have a feedback mechanism of what is an acceptable amount of risk with all of these models, and you begin to educate the marketplace on the risks associated with these models. This is consistent with the EU Artificial Intelligence Act. This is what For Humanity advocates for in our risk management framework and in our audit criteria, is the acceptance of these residual risks when you put a model out in market, and then a disclosure and transparency around those residual risks.
That's excellent. I really like that frame. Okay, Do we have any questions from the audience?
Well, I
questions
have a
from
thought
Chris?
I'd like to introduce, as usual.
Yeah, go, Chris. What do you got?
So, in my thinking, one of the major algorithms that dictates everything that we talked about is our current form of doing capital formation, right? So, because as a for-profit company, specifically if you're a publicly traded company, you have certain objectives, and they're basically written into law and then written into your corporate bylaws. So let's call it, by a matter of simplification, you need to increase shareholder value. So, and that by and large doesn't always align with whatever products or services you offer to the public. And the usual example I make for that is, even though Google, for the longest time, I don't think they're using this motto anymore, is promising to not be evil. Well, it obviously promises their shareholders something else, and that's a different objective, right? So I promise not to be evil, but I promise to increase shareholder value. And the way I create shareholder value is I sell social engineering as a service solutions to my actual clients, because you use are actually a product that I'm selling to my actual clients. So point there being is, so this particular entry point is my main issue. I think a lot of the externalities that we're experiencing are actually a subset of that particular algorithm, because it ignores all the externalities it creates, right? So then we don't account for that. So we all waste our time online finding information that's buried on purpose, and our eyeballs are being directed on purpose to certain directions that don't serve us. Larger point there being is, I don't get to set my objective. But I don't get to say, this is how I want to feel, or this is like, I want to be smarter after I do things, or I want to be healthier, I want to be happier, and so forth. I think we did a really, really bad job integrating human objectives into technologies overall, right? Not only information technologies, but all other technologies. Anyway, so the question to both Ryan and Krishna would be, how do we fix that? I have thoughts on that, but before I introduce those, I'd like your thoughts.
Let me tackle that one first. We have kind of a mantra here that when safe and responsible AI are profitable, and dangerous and irresponsible AI are costly, that's when humans win. Now, how do we change that equation? Currently, we have a massive risk-reward problem. So let's take biometric data, right? Biometrics make things easy, fast, efficient, cheaper for companies, profitable, right? Meanwhile, the human takes all of the risk of showing and donating their biometric data. Risk-reward imbalance like crazy. And this happens time and time and time again with AI, algorithmic, and autonomous systems. There's only 3 ways to fix it. Number 1, introduce government regulatory laws and enforcement, right? We have those. Enforcement is light, enforcement is difficult, and laws are reactive after the fact, punishing those who've broken the law when people have already been hurt anyway. So there's shortcomings to that. Independent audit can help fix that with proactive compliance. The second is a US hallmark, which is the private right of action. When we can raise the cost of producing these systems, then we can get a better balance of this risk-reward profile. Private right of actions, where you can sue for damages, allows the human user, but unfortunately, again, after the fact, after they've been harmed, right, to recoup damages and thus build and raise the cost structure inside of entities. And one thing I didn't know about these private rights of action is that the settlement agreements often include legally written in remediations. So that's for humanity's role to play in these private rights of actions, is to provide what that remediation should look like. And what's valuable about that is those judicial settlements often turn into policy and law. So that's part 2. Part 3 is we have to change consumer behavior. Consumers have to get smarter. Consumers have to choose responsible AI. They have to choose DuckDuckGo over Google if they want to improve their privacy in vis-a-vis search engines, right? And so that's a long-term educational process, not dissimilar to what we went through with tobacco and cigarettes, where we have to grow and change consumer behavior so that they're the ones who are choosing safe and responsible AI, and thus making it profitable, thus making it sustainably profitable over the long run.
Yeah, I want to talk a lot more about the remediation part, but first I want to hand the mic over to Krishna.
I resonate a lot with I think what Ryan just said. So the analogy I can think of is just like the security community took up this mantra of security by design after a series of data breaches and privacy breaches. I think in the machine learning and AI community, we have to adopt this notion of responsible AI by design, as opposed to viewing fairness or privacy or explainability as an afterthought. And we have to create mechanisms to incentivize organizations to do that. As Ryan alluded to, regulations are a great forcing function. But in addition to this, I often emphasize that even in domains where the technology may be somewhat hidden or may not be easily accessible, it's in the best interest of an organization to proactively monitor for bias or for explainability, and also monitor the models once they're deployed. Because otherwise, if somebody is really determined, as the Apple Goldman Sachs credit card example showed, it's possible to audit such systems even if they are not online services. And that can cause reputational harm, potentially legal harm. And it's better to preempt those and proactively pen test or stress test the models, and also monitor the models so that you don't incur potential loss of business metrics or revenue because the model is degrading over time.
All right, we're at the top of the hour. I could do this for another hour easily. I have so many more questions and ideas, but we'll try to keep this at an hour. We're going to share the content. We're doing this every Friday, and we'll keep doing it until people start listening. or the obvious people stop listening, I guess. Anyway, Jeff, do you want to lead us out?
Yes. Sorry, I muted myself.
I saw that.
Thanks, Chris. Yes, thank you to our guests, Ryan Carrier and Krishna Kentapati from Fiddler AI. Ryan's, of course, from For Humanity. This has been session 14 of Your Rights, Your Bytes. Actually, I think that's Your Bytes, Your Rights. I can't even get the show name right. How many episodes have we done?
14. So
not enough.
We'll
Jeff,
do
not
another
enough.
14, and we'll get it right eventually.
That's hilarious. Anyway, check back with us next week for another great show. Thanks again and everybody have a great Memorial Day weekend.
Thanks, Jeff. Thanks, Krishna.
Thank you.
Thanks, everyone.
Take care, guys.